Okay, so this is your course Nature and Properties of Materials, and week 1 is Introduction to Engineering Materials and Mechanical Properties. So this course is run by Professor Vishak Bhattacharya from Department of Mechanical Engineering, IIT Kanpur, and I am TA Alka Jangid from IIT Kanpur. So in first half an hour I'll be solving the questions similar to your assignment problems, and then I'll be going through some lecture slides. So I'll be starting with the example questions. So here's the first question. First I'll be checking whether someone has joined. Okay, so for the first question is in a standard tensile test near the elastic limit zone. So now there are options are tensile stress increases in linear proportion to the stress. Second option is tensile stress increases at a faster rate. Third option is tensile stress decreases at a faster rate, and fourth option is none of the mentioned. So out of these, which one should be the answer? You should guess, and answer is C. So we can explain this using here, like in stress strain curve, when we see up to elastic limit zone here, up to this, these are proportional. Stress and strain are proportional, and after that tensile stress decreases at a faster rate here, and your strain compared to tensile strain. So here it is written, during tensile testing, if the material is stressed beyond elastic limit, the tensile strain increases at faster rate as compared to the stress. So your tensile strength will be decreasing at a faster rate. So answer will be C. So now question second. So here, during tensile testing of a specimen using a universal tensile testing machine, the parameters usually measured includes, first option is true stress and true strain, second option is Poisson's ratio and Young's modulus, third option is engineering stress and engineering strain, and fourth option is load and elongation. So for this one, we know that when we do tensile testing, we measure load and elongation. So this will be the answer, and it can be explained as, like in tensile testing, load and elongation are measured, and other parameters such as engineering stress strain and true stress strain are measured by using load and elongation. So in case of engineering stress strain, we'll be dividing load and elongation by original cross-section area and original length respectively, and for getting to stress and strain, we'll be dividing them by using instantaneous cross-section area and instantaneous length respectively. Now third question. Now these are 4 statements given. Now which statement is correct? So out of these 4, only one statement is correct. So first statement is necking starts at the yield point. Second statement is yield point phenomena are seen in aluminium. Third statement is endurance limit can be determined by tensile testing. And fourth statement is yield strength is structural sensitive property. So out of these, only one statement is correct, and answer is yield strength is structure sensitive property. Now it can be explained by that if we have a steel and we are applying annealing, normalizing and hardening to three different steels with same composition. So we'll be seeing that these all three will have different yield strengths. So yield strength of material changes with microstructure because these three will have different microstructures. And other statements can be corrected by using that necking starts at the yield point. No, it doesn't start at yield point. It starts at ultimate tensile strength point. And second is yield point phenomena are seen in aluminium, and the explanation can be given as yield point phenomena are seen in alloys with small amounts of interstitial atoms such as mild steel. And third statement is endurance limit can be determined by tensile testing. No, it can't be determined by tensile testing. It is determined by using fatigue testing. While tensile testing gives us tensile properties such as elastic modulus, engineering stress and engineering strain and yield strength. Now fourth question is what is the ratio of, one second, I'll be checking whether someone has joined. Okay. Okay, so fourth question is what is the ratio of Young's modulus of elasticity to the modulus of rigidity in terms of Poisson's ratio? So we know that all these three have a relationship, Young's modulus, modulus of rigidity and Poisson's ratio. So what should be the ratio? So answer, you can calculate it and choose particular answer. So answer is A. It is 1 plus 2 times the 1 plus mu. So explanation can be given as like the relation given is E equals to 2G 1 plus mu. So here your E is elastic modulus, G is shear modulus and mu is your Poisson's ratio. And we can get if we take G to the left side, so we can get the relationship as this 2 1 plus mu. This will be your answer A. Now fourth question is Rockwell test utilizes blank a measure of hardness. So here it will be the load, depth of indentation, diameter of indentation or time of loading. So what do you think should be a measure of Rockwell hardness test? So the answer will be depth of indentation. So why will it be depth of indentation? We can see in the explanation that in case of Rockwell hardness number, the formula is given as n minus hd, where n and h are scale factors which depend on which scale we are using, like A, B, C, D. There are different scales in case of Rockwell hardness testing. And small d, it is depth of penetration in mm. Here the H value is 500 for scales B and C. So when the most common scales that we use are B and C scale, and in these case value of H will be 500 and the value of N will be 130 and 100 for scales B and C respectively. So we can say that Rockwell hardness number depends on depth of penetration. Now question number 6. Which materials are around 95% porous? So first is aerogels, second is piezoelectric materials, third is amalgams, fourth is nitinol. So out of these, which one do you think has 95% porosity in them? So the answer will be aerogels, and we can explain it by saying that aerogels are 95% porous, so as the name suggests, aerogels, and hence they are very light materials. And in case of piezoelectric materials are smart materials which convert mechanical stress into an electric signal and vice versa. And amalgams are mixtures of mercury and other metals used as dental fillings. And nitinol is also an alloy of nickel and titanium. So correct answer is aerogels. Now question number 7. It is, which of the following is not a biomaterial? So okay, so question 7 is, which of the following is not a biomaterial? So your options are PMMA, gold, lead and calcium phosphate. So out of these, which one do you think is not a biomaterial? So answer will be lead. So we know that biomaterials, we can define them as the materials which can be used as a body implants or as bone implants, dental implants, etc. So out of these, lead is toxic in nature. So lead is toxic to human body, so it can't be used as biomaterial. While other materials such as PMMA, which is polymethyl methacrylate, and gold, calcium phosphate, these all can be used as biomaterials and they don't have any toxic element to them. Now question 8 is, the hardness of material is the resistance of a material against, and your options are oxidation, indentation, twinning and fatigue. So please type your answers in chat box if you know the answer. I hope I'm audible. Okay, so answer is indentation. Okay, so the hardness of material is resistance of a material against indentation, and other options are oxidation, twinning and fatigue. So we can explain it by saying that hardness is defined as the resistance of a surface of material against plastic deformation. True, and this plastic deformation can be using either indentation or by using scratch. And other option is oxidation, and oxidation resistance is a chemical property of material, so it won't be the answer. And fatigue resistance is also different from hardness, and it is obtained by using fatigue test. And twinning is also different because twinning is one of the type of plastic deformation in HCP and FCC materials. Now question 9, it is, the ratio of elastic modulus and shear modulus is 3. The ratio is given 3, and then what is the Poisson's ratio? So you have to calculate Poisson's ratio based on this ratio of elastic modulus and shear modulus. So previously we saw the relation between elastic modulus, shear modulus and Poisson's ratio. So based on that you can calculate this easily. So this is your relationship. E equals to 2g 1 plus mu. Based on this, you can calculate what will be your Poisson's ratio. So please try to calculate and let me know in chat if you know the answer. Okay, so answer is as given here in the explanation. Answer will be 0.50. So it can be calculated using the formula that was given earlier. So we can put Poisson's ratio at one side. We'll be getting the relation y by 2g minus 1. Y here is your elastic modulus and g is shear modulus. So their ratio is given 3. So 3 by 2 minus 1 will be 0.5. So this is the last question. 10th question. Luder's line are associated with. Now your options are local plastic deformation under tensile stress and elastic zone. Third option is high hardness surface and fourth option is high toughness region. So out of these, which one do you think will be answer? Let me know. So all of you who have joined late, I'm solving questions, some examples that are similar to your assignment questions.
Okay, ma'am.
Okay. So let me know if you know the answer of 10th question. The screen is visible, right?
Yes, ma'am.
Okay, so 10th question is Luder's lines are associated with. So your options are local plastic deformation under tensile stress. Second option is elastic zone and third option is high hardness surface. Fourth is high toughness region. So answer will be your local plastic deformation under tensile stress and it can be explained using this particular okay, so these are the Luder's lines, these Luder's bands. These are formed when we deform your material, but after elastic deformation, when initiation of plastic deformation occurs. At that particular time, your local plastic deformation will occur. So these bands will form there. These are known as slip bands. Okay, so I have discussed questions. I can show them one by one so that those who have joined later they can see. So first question was this and okay, I'll be going through them. And second question, third question, and fourth question was similar to your later questions. And Rockwell hardness, then aerogel, that is 95% porous, then biomaterial, lead won't be here because it is toxic, and hardness is resistance to indentation. Then ninth question will be similar to your earlier questions, where Poisson's ratio, elastic modulus, shear modulus all have some relationship. Based on that, you can calculate it will be 0.50. And last one is Luder's lines. Now I'll be going through some lecture slides. So, okay. So, firstly, we'll be going through history of materials, then classes of various engineering materials. Then we'll be talking about mechanical properties of materials. So, if you have any queries, please raise your hand and let me know if you have any query. You can unmute yourself and go ahead if you have any queries, okay? Okay, so firstly, history and evolution of materials. So we know that materials are rooted in our culture, and they have influence over virtually every segment of our life. So, like if there is particular materials that we are using currently, they will be used in most of our industries. Like for example, transportation, housing, clothing, communication, recreation. These are some areas where these materials will be required, and early civilizations all have been designated by materials, like some dominant materials will be there for particular eras. So first is Stone Age, second is Bronze Age, then Iron Age. Initially, humans they used stones, then they could melt and forge some materials. They moved on to bronze. Then iron has higher melting point. Steels they have higher when they could melt them. Then they moved on to steels. Now, for the Stone Age, we can define as the Stone Age was coined in the late 19th century by the Danish scholar Christian J. Thomson. So, it roughly extended from 15,000 to 2000 BC. Then, it can be characterized by the creation and use of stone tools. So, in this age, humans used stones to make tools and weapons. Then wood, bones, and other materials were also used, but they had shorter life compared to them because they erode less compared to other materials, and they don't get affected by humidity. Then other age is Bronze Age, so it roughly extend between 3500 to 500 BC, and it is beginning of metal working. So when we figured out how to metal work, then we moved on to bronze. And bronze is alloy of copper and tin, and it creates this alloy, and it is stronger than other two metals individually because your solid solubility is there, and it will give you solid solution strengthening. Now these are used for as weapons and armor, decoration, etc. And these are some daggers and knives, swords. These are made using bronze. Then Iron Age, which is last age of the archaeological sequence of this 3-age system, and the Iron Age began between about 3000 years ago, and it continues today, and the use of iron and steel has changed drastically human development. So we use steels dominantly in today's scenario. Like we have witnessed the industrial revolution also, and it has improved modes of transportation, and we use it in automobiles, railways, and aeroplanes. And one of the example of this is iron pillar, which hasn't corroded till today, which was it is 7 meter tall and zero point 0.4 meter diameter and weighs around 6000 kg, and it is made of wrought iron which has high phosphorus content. And the reason it is still corrosion resistant, it is because it has a layer of crystalline iron hydrogen phosphate hydrate, and it protects it from the highly polluted atmosphere from even getting corroded in that particular atmosphere. Now, modern era in steel making. In 1855, Henry Bessemer he used steel mass production with Bessemer converter, and here air blast was injected into molten pig iron. Pig iron is has high impurities and carbon ranges from 3.5 to 4.5%. And to reduce this carbon content, we use this air blast at high temperature, and then it becomes your steel which we use. And this process is suitable for phosphorus free ores. So in 1860 Gilchrist Thomas process it was introduced, in which we improved this Bessemer process by using limestone. So limestone will be removing your extra phosphorus. So we could also use ores which had high phosphorus in them. In 1865, Simmons Martin he coined the term open hearth process. So it complemented the Bessemer process as melting iron bar or steel scrap with pig iron. So we use some steel scrap. So it will dilute the carbon percentage in final product, and it also reduced content was reduced by dilution and oxidation. Then in 1953, basic oxygen steel making, and in this we used oxygen blast instead of air blast which we used earlier. And latest we use electric arc furnace which is highly efficient and recycler of steel scrap. In it we use steel scrap and we melt it and make new product. Now steel can be recycled endlessly with no detrimental effect on its properties, and all steels created as long ago as 150 years can be recycled and used in new products and applications. Now engineering materials have
One
main,
second.
yeah,
So in the last slide you mentioned about the Siemens.
yeah, Siemens Martin.
Yeah, this is the same Siemens which we are using for our silicon conversion from metallurgical grade silicon to electrical grade silicon.
No, it is for
Same.
steel making. It is not for,
Okay, okay. No, I'm asking the person who found out this steel making
yeah,
same that is different.
that should be different. Like in Siemens is also one of the units, right? And
Okay.
yeah, so this one is different in steel making.
Okay.
Okay, so you know that engineering materials has mainly five classes. So metals, non-metals, ceramics, polymers, and composites. So in case of metals, they can be classified into two ways. First is ferrous and non-ferrous. So in case of ferrous, these will have base metal will be iron. So these can be steels, cast irons, or other alloys of iron. In case of non-ferrous, these can be copper, aluminium, titanium, gold, silver, and tungsten, and other metals and their alloys. In case of non-metals, these can be in different states. So it can be having gaseous state, liquid state, or solid state. So in case of gaseous state, hydrogen, helium, nitrogen, oxygen, these are some non-metals. And in case of liquid, bromine will be there. In case of solids, carbon, phosphorus, sulfur, selenium, and iodine. These all will be your non-metals, which will be in solid form. Now in case of ceramics, these will be compounds of metals and non-metals. So one part will be, or these can be made of entirely one thing also, like diamond, it is made up of carbon, and graphite also. So these will have very high melting temperatures. So alumina, silica, silicon carbide, diamond, graphite, these are some ceramics. And polymers can be either natural like wool, silk, which are found in nature, or these can be man-made also like polyethylene, PVC, nylon, bakelite, etc. And in case of composites, these can be wood, concrete, fiberglass, CFRP, which is carbon fiber reinforced plastics, and GFRP is glass fiber reinforced plastics. Now we'll be going through these material classes. So first is metals. So these are some of the examples. So metals can be characterized by the following properties. So if you have a lot of materials given to you, if you know these properties, so you can classify them into metals. So in case of physical properties, these will be having good electrical and heat conducting properties, and these will be malleable. Malleability means you can beat them into thin sheets. And these will be ductile, which means these can be stretched into wires, and these possess metallic luster. So luster you can see in all of these metals, and these will be solid at room temperature except mercury. And chemical properties, these usually have 1 to 3 electrons in their outer shell. So they'll be donating electrons rather than getting them, which is in case of non-metals. And they will lose their valence electrons easily. And from oxide, these form oxides. So if they are forming oxides, those will act as basic. And these are good reducing agents because they lose their electrons easily, and they have lower electronegativity. Now these are some of the examples like cast iron, wrought iron, aluminium. All alloys will also be counted as metallic materials. Now in case of non-metals, they will have like physical properties almost opposite compared to metals. So these will be poor conductors of heat and electricity. These will be brittle if they are in solid format, such as diamond, coal, and these will be non-ductile, and these do not possess metallic luster. And if they are in thin sheet, most of them will act as transparent. And solid, liquid, and gases at room temperature, they won't in case of metals they were mainly solids, but these can be in form of liquids and gases also. In case of chemical properties, these usually have 4 to 8 electrons in their outer shell, and these will gain or share valence electrons easily. And if they are forming oxides, these will be acidic, such as sulfur oxides, carbon oxides. These will be acidic in nature, and these are good oxidizing agents and have higher electronegativity. They will try to gain electrons. Now ceramics. Ceramics materials are inorganic materials made from compounds of metal and non-metal. So as I told before, one part will be metal and one part will be non-metal. These are formed by action of heat and subsequent cooling, and these are brittle in nature and a good insulator of heat and electricity, and these have excellent compressive strength. Some of the applications of ceramics are like in forming roof tiles. Silicon nitride and silicon carbide, they can also be used in making bearings, and ceramic coated turbine blades. In case of if we coat this on various things, it increases their corrosion resistance. And pottery, they are also made using ceramics. Now other class is polymers. These are polymers are large molecular large molecule composed of many repeated subunits, and these can be either natural or synthetic. So natural can be shellac, amber, wool, silk, and natural rubber, and synthetic polymers will be synthetic rubber, bakelite, neoprene, nylon, polystyrene, and polyethylene polyvinyl chloride. These are some of the applications in making like your spoons, this tire, bottles, and this helmet. In case of composites, they are generally mixtures of different categories of engineering material classes. So these can be mixture of either metal, polymer, like that. So two or more constituent materials with significantly different properties, which after combination produce a material with characteristics different from the individual components. So their characteristic will be different from their individual parts, and the individual components remain separate and distinct within the finished structure. So they will have a physical boundary between them. Okay, so this is fibers and this is matrix. This matrix can be metal or it can be polymer. So by combining these, we'll be getting composites. Now advanced or exotic materials. These can also be called smart materials. So these can be defined as like which can change the physical properties in a specific manner in response to specific stimulus input. So this input can be like providing some photons, providing some electrical field or magnetic field, and these physical properties change. These can be like they can change their color, they can change their shape, etc. And now these can be classified into various parts, but we'll be focusing mainly on four type of smart materials. First is piezoelectric, which generates an electric charge in response to applied mechanical stress and vice versa. So like we can apply a mechanical stress on material and then it can produce some electric voltage as well. In case of magnetostrictive, it will be changing its dimension and ferromagnetic materials in a magnetic field. So we'll be applying some magnetic field, it will be changing its dimension and vice versa. Phase transition dependent. In this case, these are shape memory alloys which remember their original shape, and after being deformed, it returns to its original shape if we change this temperature. Now electro and magneto-rheological materials. Rheology is related to viscosity. So if we are applying electrical field or magnetic field, these can change their viscosity. Now this is the example of shape memory alloy. So in case of martensite to austenite transition, in this we can see this type of shape memory effect. Now one of the class of materials is biomaterials. So these are substances including food or drugs which we can consume and which will be compatible with human body. So these are introduced into a living body with the aim of improving or either replacing a diseased, damaged or lost tissue or a whole organ. So example of some of the biomedical applications. So these materials which are biomaterials, these can be used as joint replacements, bone plates, bone cement, artificial ligaments and tendons, dental implants for tooth fixation, blood vessel prosthesis, heart valves, skin repair devices, which are artificial tissues, cochlear and contact lenses, pins and screws for fracture stabilization. Now, biomaterials can be made of either metals, polymers, or ceramics. These are some of the examples. So, cobalt and chromium alloys, these and stainless steels, gold, titanium alloys, these all should be highly corrosion resistant in nature. Otherwise, if it is corroding in presence of our in our body, it can produce some toxins. And beryllium, which is cobalt, chromium, molybdenum alloy, amalgams, which is mercury based alloys, shape memory alloys such as nitinol, and cobalt zinc aluminium alloy. These can be used in as orthopedics, dentistry, stent, etc. And others are polymers. These are silicons, polyethylene, and polyurethanes, polymethyl methacrylate PMMA, which was asked in question, and these are used as bone cement, uh, as it will be filling space between bone and implant, and these can be used as orthopedics, artificial tendons, vascular grafts, facial or soft tissue reconstruction. In case of ceramics, alumina, calcium phosphate, which is used for bone grafting, synthetic hydroxyapatite, which promotes bone and growth so tissues can grow easily on bones, pyrolytic carbon, which is used as lining on blood contacting prosthesis. And this is the stent that we use in heart valve to remove any blockage that is there. Now, other category of materials is aerogels, and as the name suggests, air and gels. So, aerogel is a material that is around 90 to 95% porous. So, it will be highly porous. So, they are produced by extracting the liquid component of a gel through supercritical drying. So, the air molecules trapped inside the gel would act as insulators, and its heat conductivity is close to zero because air is insulator of heat, so it will act as heat insulator. Some of the applications, these are used for capturing space dust from comets, and it is also used as insulating material in space suits. So that of NASA astronauts since 1960s. And potential applications includes thermal barriers, like in extreme cold region, clothes such as for sea urchin requires around 500 grams of gel to coat a jacket. So these as very light and also providing some heat insulation. And thermal insulators for cryogenic fuel tank for rockets, and acoustic insulators, building and pipeline insulation. These like soundproofing also one of the application of these. Other category is superconductors. So these are some element. It can be directly an element or intermetallic alloy or a compound that will conduct electricity without resistance below a characteristic critical temperature, which is symbol is Tc. So below this temperature, this material will have zero resistance. These are costly due to cryogenic requirements, because at which temperature they become superconductor, to maintain that temperature, it is very costly process. So some of the examples are mercury, lanthanum, barium, copper oxide, niobium, tin, yttrium, barium, copper oxide. So these are some materials which act as superconductors. CNTs. CNTs, carbon nanotubes, which are uh, relatively new materials which were discovered in 1991. So these are composed of carbon atoms linked in hexagonal shapes. So as you have read about graphite, so one of the graphite sheet, if we take it and we fold it in such a manner that it becomes a tube type of structure. So it with here each carbon atom is covalently bonded to three other carbon atoms, and it will have free electrons as well. So carbon nanotubes have diameters as small as 1 nanometer and lengths up to several centimeters. These carbon nanotubes are the strongest and stiffest materials yet discovered in terms of tensile strength and elastic modulus respectively. So these have very high tensile strength and elastic modulus, and these are at least 100 times stronger than steel but only 1/6 as heavy. So they have very high specific strength, and these are also extremely high thermal conductivity, which is 10 times of copper, and electrical conductivity is 100 times of copper. And these are combining carbon nanotubes with other materials into composites can be used to reinforce and build lightweighting structures. So because they have high elastic modulus, they can be inserted inside some metals or polymers to increase their strength and elastic modulus. Now, classes of property affecting product design. So some of the classes of various properties. So various properties are, they are categorized under some classes. So for example, economic and environmental properties. These can be price and availability of particular material, can be recyclability, and it can be sustainability, can be carbon emission. Carbon emission can be related to the manufacturing process. So other class is mechanical property. So in these, modulus, Young's modulus or different type of modulus, and yield and tensile strength, hardness, fracture toughness, fatigue strength, creep strength, damping. These are some of the mechanical properties. Then there can be thermal properties, which can be thermal conductivity, specific heat, thermal expansion coefficient. So, and other four can be general physical, which is density. Density is very important property which we'll be considering when selecting materials for vehicles and some aeroplane or like that, where fuel is required and fuel consumption is very critical to them. And fifth is electrical and magnetic properties. So in these, they can be resistivity, dielectric constant, which is important in capacitors, magnetic permeability. Sixth is environmental interaction. It can be oxidation, corrosion, and wear resistance. And seventh is production. So material should have ease of manufacturing, should be easier to join, it should be easier to finish. These will provide some higher rate to production. Aesthetic can be related to the color of material, its texture. These can be aesthetic properties. So now we'll be talking about mechanical properties. So some of the important mechanical properties are tensile strength, ductility, brittleness, resilience, toughness, and impact strength. This is the stress strain curve. So initial part is elastic part. So when it is proportional, this stress is proportional to strain. This part is known as elastic part, and after this it is plastic region. So it is up to UTS point. This part is known as uniform plastic deformation. So here whole part will deform uniformly, and after this necking will take place, so it is non-uniform plastic deformation. Now, why we need to determine mechanical properties? So this is the tensile testing machine. So we are capturing some data, stress strain curve, and by using these we can get a lot of mechanical properties. But after getting these properties, we can select material based on that. Like if we want to make, for example, a bearing material, so for that we need to optimize some properties. Like in case of bearings, we require fatigue strength, so those properties can be optimized. Then finally we can design that material and use that. Now, stress and strain. So, when we are performing a tensile testing or compressive testing, these two properties are important. So, first is stress. So, the internal resistance force per unit area acting on a material. So, when we are straining a material, our material will be resisting this strain, so it wants to stay in that particular form, so resisting force will be known as stress. So it uses the original cross section area of a specimen and is also known as engineering stress or conventional stress. So when we are dividing it with original cross section area, it will be your engineering stress, and its unit will be Pascal or Newton per meter square. In case of strain, it is defined as the change in length per original length. So we'll be dividing it by original length. It is unitless because length divided by length, and it is also known as engineering strain or conventional strain. And sometimes strain is also expressed in microstrain. So when strain is very low, so we use this microstrain. Now this is very important, this Hooke's law. So in this, when initially you are deforming for lower strains, so there will be stress will be proportional to strain. So within the elastic limit, low strain value will be there, so the stress is directly proportional to strain, and the behavior of solid is linear elastic, and the constant of proportion is called elastic modulus. So this E which comes in the equation, it is elastic modulus, and it is also holds good for stresses and strain in simple compression. So when we are applying compressive stress, then it will also show for particular strain it will hold this proportional limit. In the same way, shear stress is proportional to shear strain. So here this constant will be shear modulus. And in case of pressure, when we use pressure, then the dilation, the negative or dilation, these will be proportional. So the constant will be bulk modulus, which is symbol will be K. Okay, so all these three moduli will be K, G, E, all will be having dimension same as stress, which will be Pascal in gigapascal, megapascal, etc. Now elastic limit. In this graph, up to this point it will be elastic limit. So up to which your material will recover its initial shape and size. So the greatest stress that material can withstand without any measurable permanent strain after unloading. Okay, so and yield strength, the stress at which a material begins to deform plastically. So these will have particular separation, and yield strength can be determined also by stress corresponding to the intersection of a stress strain curve and a line parallel to the elastic line offset by a strain of 0.2%. So we'll be drawing a parallel line, so where it up from 0.2% strain, so it will be drawing a parallel line, so where it will be intersecting, that will be given as yield strength. Now tensile strength or ultimate tensile strength, it is corresponding to maximum load. So up to here, where we'll be getting maximum load divided by original area, will be getting UTS. And for ductility, these are the formulas. It can be in form of elongation, where change in length divided by initial length, it can be multiplied by 100, so it will be percentage elongation and percentage reduction in area. This is also one of uh, this is also ductility. So in this case, final area minus initial area divided by initial area multiplied by 100, so it will give percentage reduction in area. Now previous yeah.
I have one doubt I have a doubt regarding the difference between the elastic limit and proportionality limit.
Okay, so a proportionality limit up to which it will be proportional. Okay,
Stress
so
is proportional to strain.
up to which particular point it will be proportional. Okay, and after some time it can deviate from proportionality, but still it can remain into elastic limit. It still will, okay, it still will be elastic strain, it can recover itself.
Okay.
Okay, but when we test materials for that, we can't generally distinguish them because we don't have that much resolution in our equipments, but these are different theoretically. Okay,
Okay.
now we have already gone through engineering stress and engineering strain. In case of true stress and true strain, here we'll be dividing this load and elongation by instantaneous cross section area and instantaneous length. So the true stress strain curve gives a true indication of deformation characteristics because it is based on instantaneous dimension of a specimen. And in case of engineering stress strain, stress drops down after necking. So this will be your stress strain curve of engineering. So here it will drop after necking because we are dividing by original area. And in true stress strain curve, the stress however increases after necking, so it will keep on increasing since cross section area of a specimen decreases rapidly after necking. So because we are dividing it with instantaneous area, so instantaneous area is also decreasing, so it will keep on increasing as your stresses keep on increasing because of strain hardening. Now the flow curve, this is known as flow curve for true stress strain, and in this region of uniform plastic deformation can be expressed by the simple power law. So it can be expressed as sigma t equal to k epsilon t to the power n. So this particular before necking, it can be given using this formula. Yes. Do you have any query? Okay, so here K is strength coefficient, N is strain hardening exponent, and N can be from 0.5, 0.1 to 0.5 for most of the metals, and it will be 0 for perfectly plastic solid, and it will be 1 for elastic solids. Now other properties are ductility and brittleness. So for ductility, it is measure of degree of plastic deformation that has been sustained at fracture. So up to fracture, when we measure what elongation that has happened up to that particular part, it will be known as ductility. So it will be your percent elongation. So if a material has percent elongation more than 5%, so it will be known as ductile material. It will have a well defined yield point, and if a material has elongation less than 5%, then it will be known as a brittle material, and it won't be exhibiting some identifiable yield point. So this is a white cast iron. It will be showing a brittle fracture. So it won't be showing necking type of behavior. While this is a ductile failure, so here it will be showing necking, and the method ductile failure, it takes place with help of void nucleation and void coalescence in this format. Now resilience, it is your area under the elastic part of the stress strain curve. It will be known as resilience. So resilience is capacity of a material to absorb energy when it is deformed elastically and then recover same upon unloading. So this can be recovered when you will be unloading your material. And modulus of resilience, which is strain energy per unit volume, it required to stretch a material from an unloaded state, which is here, to the point of yielding up to yield point. So it is a triangle. We can approximate in form of triangle, and we can say its formula as half times this, which is sigma y yield strength, multiplied by epsilon y, which is strain at this point. So this formula can be given for modulus of resilience, and strain can be written by using Hooke's law as sigma upon E, elastic modulus. So this formula can be given in form of sigma square divided by 2E. Now resilient materials have high yield strength and low modulus of elasticity. For example, beryllium copper, and this material is used for making spring materials. And resiliency is very important property in case of spring materials. Now toughness will be your area under entire stress strain curve. Now it is the measure of ability of a material to absorb energy up to fracture, and it is represented by total area under the stress strain curve up to the fracture point. And brittle material has comparatively high yield and tensile strength but low toughness due to lack of ductility. So this is brittle material, which will though have high yield strength, but it will have low area under it, while ductile material will have high area below it, so it will be tough. And ductile materials are tougher than brittle ones. Okay, so which can be seen from this graph. Now one of the another mechanical property is impact toughness, and it is measured using impact testing. So Charpy and ISO, these are two methods which are used for measuring it, and in these tests load swings from a given height to strike the specimen, and the energy dissipated in the fracture is measured, and the metallic samples tend to be square in cross section, while polymeric materials, they will be in rectangular shape. Now impact testing shows that in case of ceramics, these will be having lowest impact toughness as compared to polymers, they will have higher impact toughness, and then composites and pure ductile metals, these will have highest of the impact toughness. Now, factors which affect impact energy. Firstly, for a given material, the impact energy will be seen to decrease if the yield strength is increased. So, yield strength is increasing, impact energy will decrease. And the notch serves as a stress concentration zone. And some materials are more sensitive towards notches than others. So, if a material is brittle, then it will be highly sensitive compared to a ductile material. Most of the impact energy is absorbed by means of plastic deformation during the yielding. Therefore, factors that affect the yield behavior and hence ductility of the material, such as temperature and strain rate, will affect impact energy. So, if we are performing this test at very low temperatures, then it will show low impact toughness, and strain rate will have similar type of effect. Like if we are increasing strain rate a lot, then it will act as brittle material and will show less of impact toughness. One of the important properties is hardness, and it is the measure of material's resistance to localized plastic deformation. And this plastic deformation can be by either indentation or scratch. Now, advantages of hardness testing. So, firstly, it is simple and inexpensive compared to like tensile testing, fatigue testing, and creep testing. And it requires no special specimen preparation, and the apparatus used is relatively cheaper. And it is non-destructive in nature. There will be just indentation formed, as compared to like in tensile testing, you'll be breaking your sample, so it can't be used further. And other mechanical properties like tensile strength and fatigue strength, they can be estimated using these hardness data to some extent. One of the oldest methods of measuring hardness was using Mohs scale. So it is based on the ability of one material to scratch another, and hardness is measured on a scale from 1 to 10, and 1 will be softest and 10 will be hardest. If this is scratch method, and when we go for indentation method, these can be divided in two parts. So one will be macro hardness test, other will be micro hardness test. In case of macro hardness test, it can be Rockwell hardness testing, Brinell hardness testing, and Vickers hardness testing. And in case of micro hardness test, there are two types of micro hardness test. One is Knoop and other is Vickers. So in case of most hardness tests, these are important. For the 1, it will be torque, and for 10, hardest material is diamond on Mohs scale. And it is mainly used for identifying minerals. Now, these are some of the hardness tests which are summarized here. So for Brinell hardness test, we'll be using a 10 mm steel ball, and for tungsten or for hard materials we can also use tungsten carbide ball. And the load that we use is either 500, 1500 or 3000 kg. For Vickers hardness, we use diamond pyramid, and it will have an angle of 135-36 between different faces. And in this we measure diagonals, and by using these average of diagonals, we use this formula to calculate Vickers hardness number. Another method is Knoop, in which diamond pyramid is used, but here diagonals of this indenter are in ratio of 7:1, and here this formula is used, and load applied is lesser compared to other methods. So here 25 gram to 5 kg load is applied, and it is because it is micro hardness testing. For various industries, Rockwell hardness test is used. Here various scales are there, like A, B, C, D, F, G. So here for ACD, a diamond cone indenter is used, which is also known as Braille indenter. Here the angle will be 120 degree, and for BFG, these use a 1 by 16 inch diameter steel ball. Here loads which are used are can vary depending on scales, and these two different type of formulas are used based on scales. Now another mechanical property is creep. In this, a permanent deformation under constant load over a period of time. It is measured, so there will be deformation and load will be constant, and at a particular time you will be seeing effect of temperature. A creep test involves a tensile specimen under a constant load maintained at a constant temperature. So both your load and temperature will be constant, and will be measuring here strain on y-axis with time. At relatively high temperatures, creep appears to occur at all stress levels, but the creep rate increases with increasing stress at a given temperature. So the applications of this particular property is studying material behavior at elevated temperatures, like such as turbine blades which work at high temperatures, and nuclear reactor components, jet engines, heat exchangers. So these all materials, before applying some materials to these should be measured for their creep strength. And this creep occurs in three stages. From this graph we can see. So first part is primary stage, second part is secondary state, in which it is almost proportional, which is known as steady state, and third part is tertiary. So in first part, the beginning of the test and the creep is mostly transient, and then second part it is almost at constant rate, and then creep rate begins to accelerate at the cross sectional area decreases due to necking, followed by failure, and failure in case of creep is known as rupture because it is ductile in nature. Now final mechanical properties is damping. So for methods of vibration reduction, so if we want to reduce vibrations in particular machine or vehicle, we can do it by two methods. So we can either increase damping capacity of material, or we can use some stiff material. So in case of damping, so damping is referred to as dissipation of energy from a vibrating system. So damping force magnitude is generally smaller than elastic and inertia forces. So even if damping forces is smaller, it is important for controlling vibration, particularly near resonance. Now this property is important in case of vehicles and some machines which are subjected to vibrations. And advantages of this particular damping capacity in materials, it can be used in shock absorption, fatigue failure prevention, and noise reduction. Now this is all. Now if you have any queries, please let me know. I'll be here. So if you have any queries, please let me know.
Madam, good afternoon, madam.
Yes.
Yeah, I joined little bit late for this class, madam.
Okay.
So this class is for any specific week related or in general, madam?
It will be it is for your queries like regarding any assignment questions. I'll be going through like example questions so that
Okay.
you can solve your assignments easily.
No, exclusively for any specific week, madam. Week 1, week 2, week 3, or in general?
This one is for week 1. Today
Week
it's
1.
for week 1.
Okay, okay. There is a small doubt in question number 2, madam.
Question number 2. Okay.
In the,
Okay.
no, this is
This
not
one.
the question in the question. No, 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 madam.
Which one?
Actually, questions are different from our
Okay.
assignment.
From your assignment. Okay. From your assignment which you are given this year, I can't tell you answers to that. I can tell you similar to that on the
No, no.
other.
Already week 1 questions are results are declared, madam.
Yeah, answers
This
are.
is for nature and properties of material course, no, madam?
Yes.
So in that assignment 1 is having different questions.
Yeah, assignment. Your assignment will have a different questions, but I'm told
Very-
to tell you answers similar questions similar to your assignment, not
But
exact questions.
but that answers for assignment 1 is released. There is a
Okay.
doubt in the question number 2, madam.
Okay. What is the question?
That is outermost layer that electrons are tightly bonded or loosely bonded. There are 4 options were given.
Okay.
But I think that answer is maybe different, madam. Actually, yesterday also I attended one session.
Okay.
There also he told that yeah, that is that should be corrected.
Okay. So, what was the answer?
I will read out that question, madam.
Okay.
So, what is the primary difference between a metal and non-metal based on their atomic structure?
Okay.
And I am thinking that metals have loosely held outer electrons while non-metal have a tightly held outer electrons.
Yes.
But when I kept that answer, it is shown as incorrect.
Okay. What was the
And
correct answer there?
that they have mentioned that metals have reverse, that is, metals have tightly held outer electrons while non-metals have loosely held outer electrons.
Okay, it should be
This
wrong.
is the
Like
question.
in case of metals, they can easily donate electrons,
Yeah,
right?
yeah, they will lose electrons, na?
Yeah.
Because of that ionization energy.
Yes.
So I think then how to correct it?
That part I'm not aware. Like, how can you raise like query to professor?
Okay.
We can put it on the forum now.
Yeah, yeah.
Okay.
Try that.
Even I went for me also.
It is
It has
showing
been
wrong.
marked. Yeah.
Okay.
Will you share this PPT, madam? It is a little bit easy for us.
Yes, yes. I will share it.
Okay.
This video will also be shared, and this PPT will also be shared.
Okay. Okay.
Okay.
So this presentation is only for the week 1.
Yeah, it's for week 1. If you have any other queries, let me know. I'll be present here till 5 o'clock. Okay.
Okay. Anything you can discuss about crystal structure, ma'am?
Crystal structure. That is second
Mm.
chapter, right?
Yes, ma'am.
Yeah, so I'll be discussing it next week.
Next week.
Do you have any particular query?
That also have some query. Diamond crystal structure.
Oh, that is
I'm
asked
having
in this week's.
you asked in that.
Yeah, I can tell you that. You have to solve on your
That
own.
okay, okay. That structure is different in different textbooks, madam.
Sir, whatever sir has taught, try to relate to
Yeah.
that.
Okay. Okay, madam. Thank you. Thank you much more.
Okay.